Hello everyone, welcome back to Stoichiometry from Chapter 8. So I'm starting with this balanced chemical equation again. It's one from a previous slide because I think it's a good introduction to this next concept that we will talk about, which is called limiting reactant. So if you recall from last time, one of the example problems was this balanced chemical equation. And I said if we have 3 moles of nitrogen and excess hydrogen, how much NH3 can we make? And at the time, I said that the fact that I stated that there was excess hydrogen would become more important later. The reason why you didn't need to know exactly how much hydrogen gas there was is because I specifically told you the amount of one reactant, specifically nitrogen gas. And so therefore you could use the information from that reactant, specifically the moles of nitrogen, along with the coefficients of the balanced chemical equation to relate moles of nitrogen to moles of product, specifically NH3. And looking at that balanced chemical equation, for every 1 mole of N2, there are 2 moles of NH3. And then setting that problem up correctly with your dimensional analysis skills gives you 6 moles of NH3. So the fact that we used the moles of nitrogen to dictate or to calculate how much product was produced, that means that the nitrogen is called the limiting reactant. Limiting reactant because that nitrogen is limiting the amount of product, specifically NH3, that is produced. So since nitrogen was limiting, and I sort of told you that by saying that there was excess of the second reactant, the fact that nitrogen is limiting, that is what is used to calculate the amount of product formed. So in this example, I didn't have to really use the words limiting reactant because I inferred that nitrogen is what should be used to calculate the amount of product by saying that we had excess or too much H2 gas. And therefore it was the moles of nitrogen gas that's used to calculate the product. So in this situation, determining which reactant to use, what the limiting reactant is when doing calculations was pretty straightforward. But sometimes it isn't as straightforward when doing limiting reactant calculation problems. And we're going to do 2 examples in a second. But I'm going to go ahead and use this example of cooking and of a recipe to kind of reemphasize the concept of limiting reactant. At first, I didn't really like this example, to be honest, but I think it is instructive because, everyone knows how to make pancakes. I know that since we have been on stay-at-home and schooling at home, my son's been wanting me to make pancakes every day. So I've been familiar with how to do that. But let's use this example of a recipe to talk about this concept of limiting reactant. I mean, the definition of limiting reactant is that a limiting reactant is what determines how much product can be made. So if I have a recipe here, let's say I have this example recipe of 1 cup flour, 2 eggs, half a teaspoon of baking powder. Those reactants, those ingredients give me 5 pancakes. Just use this as an example. So let's say I go rummaging around in my cupboard at home and I want to see how many pancakes I can make. Well, to know that, I need to know how much of certain ingredients that I need. So I go rummaging around in my cabinet and I find that I have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. And I want to know, okay, so these are all the amounts of the ingredients that I have. Here is my recipe of what is needed for 5 pancakes. How many pancakes can I make? Do I just have enough ingredients to make pancakes for myself and my son, or can I invite more people over for pancakes? Although I shouldn't do that during this time, but I want to know, how many pancakes can I make? Well, if I use my flour information along with my recipe to calculate how many pancakes I can make, I get 15 pancakes. Because for every 5 pancakes, I use 1 cup flour. If I have 3 cups flour, doing my little dimensional analysis, that tells me I should get 15 pancakes. But if I do a similar calculation using another reactant or another ingredient, for example, eggs. If I do a similar calculation using 10 eggs, knowing that I need 2 eggs for 5 pancakes, that shows that I could make 25 pancakes. And then if I use my baking powder information, specifically the amount that I have and what's required in the recipe, I get 40 pancakes. So the question is, which is correct? How many pancakes can I make? Can I make 15? Can I make 25? Or can I make 40? Well, the answer is 15 pancakes. And why is that the case? That's the case because after you're done making 15 pancakes, that's the smallest amount of product that's made, what happens to your flour? Your flour is all gone, right? Because you've used all 3 cups of your flour, right? So your flour limited the amount of pancakes that were made. And how did I know that flour was my limiting reactant? We knew that flour was the limiting reactant because it gave the smallest amount of product, specifically the smallest amount of pancakes. So I can feel confident with this recipe and the amount of ingredients that I have that I can make 15 pancakes. My flour is my limiting reactant because that's what gave me the smallest amount of product. And in chemistry terms, this amount of product that you get from your limiting reactant is called a theoretical yield. Okay? So limiting reactant, reactant that gives you the smallest amount of product, that smallest amount of product is called theoretical yield. Those are 2 terms that you will hear frequently in these kinds of problems. So we're going to talk through 2 examples, and then in the next video, I'm going to do 1 or 2 examples from your worksheet on Canvas. Okay. So let's say I have this example balanced chemical equation, solid titanium reacting with chlorine gas to give me titanium 4 chloride solid. And I have given you amounts of reactants in terms of moles, and I want to know what the limiting reactant and the theoretical yield is. So by definition, the limiting reactant is the one that produces the smallest amount of product. Whatever that smallest amount of product is, that is called the theoretical yield. So what that means is that I cannot just look at the amounts of my reactants that are given and say, oh, since 1.8 is smaller than 3.2, that means titanium must be limiting. No, you need to look at the smallest amount of product that is produced, which in this case is the TiCl4. So that means in these problems, you are going to have to do two calculations. One calculation will be using the 1.8 moles of titanium and determine how many moles of titanium chloride that gives you. And then you'll do a similar calculation, but in that case using the 3.2 moles of chlorine gas and seeing how many moles of titanium for chloride that gives you. So what I just said verbally is shown here. So I took my 1.8 moles of titanium and my 3.2 moles of chlorine gas, and I need to calculate how many moles of product are formed from each. And remember, anytime you go from moles of one thing to moles of something else, you use those coefficients of the balanced chemical equation. So in this example, for every 1 mole of titanium, there is 1 mole of TiCl4. So it's written like here, with my units canceling. So I can calculate how many moles of titanium for chloride. I do something similar with the chlorine, except I need to make sure to use the proper coefficients from the balanced equation for the calculation. So when I use chlorine as a reactant, I see for every 2 moles of chlorine, I have 1 mole of TiCl4. And so looking at both of these calculations, I see that I get the least amount of product when I have chlorine as the reactant, because 1.6 is obviously smaller than 1.8. So this 1.6 moles of TiCl4 is the least amount of product, so this would be the theoretical yield. And my limiting reactant would be the chlorine gas. So now note that even though I had less titanium mole-wise than chlorine gas, chlorine was the limiting reactant because it produced the smallest amount of product. Okay. So that's how to do limiting reactant problems when given moles of reactants. But many times you know that when we start a chemical reaction, we have our reactants not in terms of moles, but in terms of grams. So we can still do limiting reactant problems when given grams by using this same dance that we learned in the previous chapter, where if you have grams of one substance, you can get to moles of that substance through the concept of molar mass. So in this reaction, in this problem, let's talk through it. So we have this balanced chemical equation. I give you amounts in terms of grams of 2 reactants. And I want to know what the limiting reactant is and the theoretical yield. So anytime you see the term limiting reactant, think, oh, the limiting reactant, that's the one that produces the smallest amount of product, which in this case is going to be NaCl. So I need to do 2 separate calculations. One where I start with one reactant, the 53.2 grams of sodium, and find out how many grams of sodium chloride that is. And then in the second calculation, I start with the amount of the second reactant, specifically 65.8 grams of chlorine gas, calculate how many grams of sodium chloride that gives me, and then I compare those two, these two to determine what's my theoretical yield and the limiting reactant. So I'll talk through these 2 equations a little bit. They are using similar skills from chapter 6 when we introduced moles. But when given grams of a reactant, I can get to moles of that reactant using the molar mass of sodium. Then I can go from moles of sodium to moles of sodium chloride from the coefficients of the balanced chemical equation. For every 2 moles of sodium chloride, I have 2 moles of sodium. My units cancel. I'm left with moles of sodium chloride. Now I use the molar mass of sodium chloride. So 1 sodium plus 1 chlorine, those masses from the periodic table. And so there's 58.44 grams of sodium chloride in 1 mole of sodium chloride. I write that so my units cancel. And so then doing the appropriate math, multiply everything that's in the numerator, divide everything that's in the denominator, should give you 135 grams of sodium chloride. You'll do something similar for the chlorine Cl2 sample, but you'll just need to use the molar mass of chlorine. So 1 chlorine times 2, so 35.45 times 2. Then you'll use the coefficients of the balanced equation to go from moles of chlorine. Specifically, there is 1 mole of chlorine to 2 moles of sodium chloride. And then molar mass again of sodium chloride, so then you can find grams of sodium chloride. And so when putting this in your calculator, you should get 108 grams of sodium chloride. And so remembering the definitions of limiting reactant and theoretical yield, the 108 grams of sodium chloride, since that is the smallest amount between when comparing these two, that's going to give you the theoretical yield. And what gave us that smallest amount of product, the theoretical yield? It was the 65.8 grams of chlorine gas. So that is your limiting reactant. So that is the concept of limiting reactant and theoretical yield. I encourage you to watch this video over again if you need to, but in the next video, I'm going to be working 1 or 2 more problems from your Canvas worksheet to practice these skills of limiting reactant and theoretical yields. Have a good rest of the day, everyone.